Hello. Today I am going to start with a graphical illustration of quantile regression model. So let me start with quantile. What is a quantile? So think about a normal distribution just for illustration. So here is a normal distribution, and then there must be a point, this point where the left-hand side area equals to 10%. So then we call this point as the point 1 quantile or 10 percentile. So point 1 quantile or 10 percentile, which implies bottom 10%. The point here is we are calculating the left side area because the distribution function is defined as the probability smaller than a certain point. So distribution function is capturing this area. And similarly, like if you think about point 0.9, then to have a point 0.9 area, you have to have a point up to this point. You have to calculate this area up to this point. And then this point is called point 0.9 quantile or 90 percentile. So then its interpretation is the same, bottom 90%. But no one says it as a bottom 90%. But of course, it has to be interpreted as top 10%. So just an interpretation. So even if it is top 10%, the probability must be calculated from the bottom. And the most famous quantile is the median, which splits the distribution into 50% and 50%. So 50% is split in this example in the normal distribution. It is always the mean because the distribution is symmetric. Because the distribution is symmetric about the mean, then the median equals to the mean. Normal distribution is an example. Anyhow, this is so the definition of quantile, graphical definition of quantile, and then now let's think about non-symmetric distribution. This distribution is skewed to right. I'm using log normal distribution. You consider standard log normal distribution, and then it has a skewed tail on the right hand side. And then if you calculate the mean, it is here, but the median is here. Now the mean and the median are different because the distribution is not symmetric. But like another thing you have to understand here is not only different, but there is a pattern. There is a pattern that mean is greater than the median. So because the main problem is the tail is long on the right hand side. Then because of this tail, mean is closer to the tail. So it affects the mean more. So mean is moving to the tail more than the median. So always if your distribution is skewed to the right, then mean is on the right side of the median. So vice versa. If the distribution is skewed to the left like this, then mean is smaller than the median. Mean is smaller than the median. So it's this happens because of the tail, the outliers. So here I will show you the examples. Suppose that on the right hand side, if you think about income, say this is an income distribution, then at the end of the right side, there must be someone like this. Maybe these days, these days the ranking changed a lot. Maybe Elon Musk may be listed at the top now. Anyhow, Jeff Bezos, Bill Gates, Warren Buffett are the top three in 2019. So these guys are literally the outliers in our example. And then so they are outliers. And then think about the average. The average household income is point average income wealth. So maybe wealth, I think. Average asset a household has is about 0.7 million. per household, according to this in 2016. Then what it means here is, suppose that you are Jeff Bezos. Then if he donates all of his assets, then he can give $1,000 to everyone. So everyone can get $1,000 in the United States. So that means he can increase the average by $1,000 by himself, by one person, out of I don't know how many. So there are more than 100 million households. So Jeff Bezos is just one out of more than 100 millions. Still, he accounts for 0.1%, more than 0.1%. So as a number, he is just one out of 100 million. But in terms of income, in terms of asset, he is one out of 1,000. He's taking care of a lot in this mean. So his effect on the average is more than 0.1%, but in the probability, he counts as 1 out of 100 million. So his effect on probability is nothing, nearly nothing. Therefore, this is an intuition why the mean is more effective, more sensitive to the outliers than the median. So median is related to the probability, and the outliers are really rare. So in terms of the probability, they are ignorable. However, the small probability of outliers have a huge outcomes. Therefore, they are not negligible in calculating the mean. That is the major difference why the mean and the median are different. Here is another example. Think about this. This graph shows you the difference across different quantiles. Say top 5 quintile, top quintile. By the way, quintile is top 20%. So if you divide households into 5 groups by 20% each, then the dotted line is top 5 percentile, and the blue solid line is top 20 percentile, and this light purple line is top 40%, top 60, 80, and bottom 20%. And then as you can see, there is a huge difference across quantiles. So if you take the mean regression, you are going to get somewhere here, between maybe red and purple, somewhere near purple. But it is not wrong. The mean has increased. The mean income increased at this pace, but it is not everything in understanding the economy, and especially the income inequality. To understand the income inequality, one line, one curve cannot explain how it changed. You have to look at all the curves at the same time to see how much the inequality increased over the last 50 years. And it's quite surprising. So if you estimate quantile regression at top 5%, this will be your estimate, and this will be your top 20%. So exactly the same thing can be done by quantile regression. So quantile regression is doing something like this, right? And then also another simple example is that here, think about this strange example. Say we observe income distribution in 2000 and 2010, and suppose that the log of income follows a normal distribution. And additionally, suppose that the mean was 1 and the standard deviation was 1 in 2000, and in 2010 the mean increased to 2, but inequality increased to 2. In this case, the distribution changes from the blue to the orange. So the mean, if you use the mean regression, you will only observe plus 1. Plus 1 is the change in the mean, which is clear. However, if you look at other quantiles, say 0.1 quantile, if you think about 0.1 quantile at each time period, what is interesting here is the zero point 0.1 quantile decreased like over 10 years. So even if the mean increased, the quantile may decrease because the inequality increased. So this is a surprising result. And if you look at 0.9 quantile, your the 0.9 quantile income increased by more than 2. So the actual increase is twice more than the mean increase in the mean. So as you see in these examples, looking at the mean is not everything. So even if the mean increases, there may be some people who get different effects. So average is just an average. It does not represent everyone. So that's the main motivation of using the quantile regression, especially when you are interested in the inequality or the dispersion. And then, so using this example, if you put them in a regression model, so here 10 percentile, say 10 percentile, median, and 90 percentile. 10 percentile, median, 90 percentile. So if you use the mean regression, you will get this. This is the mean regression. But if you use 0.1 quantile, you are going to get this slope. The quantile regression estimate will be totally different. Quantile regression at 0.9 is also different. They are not parallel. They may be parallel, but in this case, their slope can be different at different quantiles. So this shows why we need to study quantile regression. So exactly this is what we see here. So the same thing can be modeled in this way. And we will learn how the quantile regression can be estimated and can be interpreted, like in this kind of case. So, and so as you see, the slopes are different if you use different quantiles. So if you are interested in the growth rate for the rich, then you may use higher quantile. But if you're interested in the growth rate for the poor, then you may use the lower quantile. If you're interested in the average, then mean regression is the best. If you're interested in if you're interested in the average, but if you are worried about outliers, then I recommend you to use the median regression. So there are many different reasons to use quantile regression in the same example. And I think I will stop here. So this is a different story. So I explained the motivation why we need to consider the quantile regression. It is really useful. You can extract a lot of information from the quantile regression than the mean regression. Okay, thank you for watching. See you later. I will go back to the lecture notes and I will do some technical explanation, and then we'll come back to this slide again later.